In this section, we're going to look at complex numbers from an algebraic point of view. Here's our first problem. We want to find x and y if this complex number is equal to this complex number. Now this number has the form a plus b times I, and this has the form c plus d times I. And the only way two complex numbers can be equal is if their real parts are equal. So I'll set 5x plus 2 equal to 4, and if their imaginary parts are equal, negative 7 equals 2y plus 1. I'll solve this equation for x by adding negative 2 to both sides and then dividing by 5. So I get x is equal to 2/5. I'll solve this equation by adding negative 1 to both sides. I have negative 8 is equal to 2y. Then I'll divide both sides by 2 and have negative 4 is equal to y. So in order for these two complex numbers to be equal to each other, it must be true that x is 2/5 and y is negative 4. And the point of this problem is that two complex numbers are equal if their real parts are equal and their imaginary parts are equal. Here's our next problem. Let's simplify this sum and difference of complex numbers. We're going to treat the I, even though we know it's the square root of negative 1, just like it was a polynomial. Or we're going to treat all of these expressions as if they were polynomials. So I'll start by taking care of this subtraction sign by changing the sign of each thing inside the parentheses. So I'll have 3 plus 2i minus 6 minus I plus 5 plus I. So I remove these parentheses. There's a negative sign in front, so I change the sign of each thing inside. Now let's say I have 3 plus negative 6 is negative 3, plus 2i minus I is just I, plus 5 plus I. And I'll continue to add the real parts. Negative 3 plus 5 is going to be 2, and then I plus I is 2i. So I've simplified this complex number, this expression right here, involving three complex numbers down to just the complex number 2 plus 2i. And I did it by treating everything as if they were similar terms. So I add the real parts which don't have the i's in them, and I add the imaginary parts which do have the I in them. Let's look at another problem. Let's simplify I to the 32. Any power of I can be written as I, negative I, 1, or negative 1. And I think I'll use the fact here that I squared is negative 1 and write this as I squared to the 16th, because I know 2 times 16 is 32, and I also know that I squared is negative 1. So I have negative 1 to the 16th power. Negative 1 to the 16th power will just be the number 1. So that power of I to the 32, simplifies to just 1. I to the 33, I'm going to do the same type of thing. I'll write this as I squared to the 16th times I. So 2 times 16 is 32 plus 1, that's the exponent right here, adds up to 33. I to the second to the 16th power I know is 1, times I to the 1 gives me just I. So I to the 32nd power simplifies to just 1. I to the 33rd power simplifies to I. Every power of I, every integer power of I will simplify to either 1, negative 1, I, or negative I. Here's our next problem. Let's expand and simplify 3 plus 2i. So I'm going to write this as 3 plus 2i times 3 plus 2i, using the fact that this exponent means repeated multiplication. Now, I'm going to multiply just as if these were polynomials. So I'll multiply the first two terms, 9, the outside terms, 6i, the inside terms, another 6i, and then the last terms, 2i times 2i will be 4i squared. So this will be 9 plus, now 6i plus 6i. These are similar terms, so I'll add these and get 12i, plus 4 times I squared, which is negative 1. So 4 times I squared is negative 1, so this is going to be 4 times negative 1, which is negative 4, plus 9 will give me 5, plus 12i. So if I square this complex number, 3 plus 2i, I end up with a complex number 5 plus 12i, and I do it by treating it the same as if it was a polynomial. So I add similar terms right here to get 12i, And then I also use the fact that I squared by definition is -1 to help simplify this last term a little bit. Let's look at a division problem. We have 2i divided by 3 plus I. So to do division with complex numbers, I do something that's similar to rationalizing the denominator with radicals. What I do is multiply the numerator and denominator of this fraction by the conjugate of the denominator. So I end up with 3 minus I times the denominator and 3 minus I times the numerator. So once I have that, now I can just go ahead and multiply. 2i times 3 will be 6i. 2i times negative I will be negative 2i squared. And in the denominator, when I multiply conjugates, I'll have 3 times 3 is 9. Positive I times negative I is negative I squared. A negative I squared is a positive 1. And then my inside term is 3i, my outside term is negative 3i, so those add to 0. So I just end up with 9 plus 1. Now I'll simplify the numerator here. Negative 2 times I squared will be positive 2 plus 6i, all divided by 10. And then I'm going to reduce this to lowest terms by writing this as 2 times 1 plus 3i divided by 2 times 5, because I have a factor of 2 common to the numerator and denominator. That divides out. And so if I want to write this in standard form for complex numbers, this will be 1/5 plus 3/5 times I. Or I could just write it as 1 plus 3i all divided by 5. But if I want to see the real part and the imaginary part here, it will be 1/5 plus 3/5 times I. So that's a look at addition, subtraction, multiplication, and division with complex numbers.